Hi, my name is Ellen, and I am here today to talk to you guys about volume by rotation using the washer method, something we use in calculus with integrals to create volumes created by region. So let's look at the question. It says, find the volume of the region bound by y equals x squared plus 1 and y equals x plus 3 as it is revolved around the x-axis. So the first thing I always do with these types of problems is draw a picture. You want to visualize, get an idea of what we're talking about. It does not have to be exact. It just has to be something to help your brain figure out what you're talking about. So here we have y equals x squared plus 1. That is a parabola that is transformed up 1. So I'm going to start our vertex here. I'm going to go over 1, up 1, left 1, up 1, and I've got 3 basic points here that I have to create my parabola. The next shape is y equals x plus 3. That's a line with intercept at 1, 2, 3. We can go up 1, right 1, down 1, left 1. Looks like I found a point in an intersection there. And we get our line. So we've created this nice little region inside of our line and our curve, some sort of bowl shape, little, unique dimension there. All right, so I do need to find where these intersect. This looks like my drawing. I can't tell what it is. So if I can't tell what it is by my, quick drawing, what I can use is the fact that these are two systems that I can solve. So I'm going to solve my systems because it's y equals something and y equals something. I can set those two somethings equal to each other. X squared plus 1 equals x plus 3. So I'm going to move everything to the left side here. Set it equal to 0 so that I get a quadratic and I can factor x minus 2, x plus 1 equals 0, x minus 2 equals 0, x equals 2, x plus 1 equals 0, zero product property in play here. So x equals negative 1, so this is actually negative 1, and this up here is x equals 2. We're only worried about our x's because we're going to differentiate with respect to x due to the fact that we are revolving around the x-axis. So yay, solve those systems. Now that I've solved the systems, I want to come up with a way to visualize what's happening. So we're going to rotate around this x-axis. What happens when I take this shape and rotate it? Bring this point up, around, and under, and around. What do I get here? I end up with a big circle, a nice blue circle here from my blue line that's being rotated. We'll start with the blue here, and look how I'm going to also draw that reflection. So those is creating the circular shape this way. Then if we get our purple involved in it, the purple circles here. Notice how I'm going to draw the reflection here as well and what those shapes look together. So remember, this would be 3D, but this is what you can put on your paper to help you visualize. Remember, this is coming out and going under and coming around, so that 3D revolution that we have going on here. So imagine for a second that I'm standing on the end of that x-axis and I'm looking down into it. What am I going to see from the top looking down? I'm actually going to see that outside blue circle, because for the most part it's the widest point of any of my part of my function. And then I'm going to look down and I'm going to see a smaller hole cut out by the smaller purple parabola that we have going on, that's going down in there. So it's kind of a nice washer here, which is why this is called the washer method, if you remember those metal cylindrical objects. So if you notice, our radius is going to be changing here because these are functions. Here our radius is smaller, it's getting bigger. But let's imagine for a second that our radius didn't change and we flipped this on its side and drew a cylinder with that hole cut out of it. That's something that we can work with. If you remember back from geometry, the volume of a cylinder is area of base times height. This being the height, the area of our base shape is a circle, so volume equals pi r squared times h. Now if I wanted to do this plain old cylinder with a hole cut out of it, I would take the volume of the larger cylinder, pi r squared, which would have the larger radius, and I would subtract the volume of the smaller cylinder, which would have a smaller radius but the same height, to find this very simple hole cut out of it area or volume of the cylinder. Now, because our radius is changing here, it gets a little bit more interesting. So let's look at what that radius looks like. So we're going to find our radii here. Our radii are going to look like this. The radii of the larger circle, the blue one, is going to go from this x-axis here. I'm going to try and draw it so you can see it. this x-axis, we're always going to go perpendicular to where we're trying to revolve around. So the x-axis all the way up here, touching the highest point, which is that line. So it's not 5, it's not 6, it's not some constant number. It's the equation of x plus 3. So the radius of the larger is x plus 3. Similarly, we're going to put ourselves on that x-axis here for the parabola. The radius of that parabola goes from the x-axis up, touching that purple parabola, and the radius of the smaller one then is the function of that parabola, x squared plus 1. So now let's take into account the area, because we're going to use, that's why we talked about this, we're going to use this area formula within there to help us with our problem today. So the area of the larger one is just going to be that pi times our radius, which we've identified as x plus 3, quantity squared. Your radius is always squared. The area of the smaller one is going to be pi times that radius, again, that we've identified, quantity squared. Well, that's great, Ellen. That's wonderful. I got area, I found the radii, I'm getting that, but how does that create volume? How are we going to get this h? Well, h is the sum of all of our areas put together. So notice how, if you recall from learning about integration, integration is the sum of the area underneath the curve. You know, we calculate one little area and add them all up. So in this case, if we want to find the volume of this, we're going to use our area that we found here under the curve, and we're going to evaluate it from -1 to 2, which were the points of intersection here. So it's a nice formula. This integration sign actually then represents the height portion of our volume formula. So here's area, this creates our height, and then if we were going to actually solve it here, we would subtract off the volume of that smaller one, which is still from -1 to 2, and the area of that is pi x squared plus 1 quantity squared. Now, our rules of integration allow us to combine these, so look at what I'm going to do. I'm going to make this -1 and 2. I'm going to make, here we've got pi x plus 3 quantity squared minus, we have pi x squared plus 1 quantity squared dx. Oh, losing all my dx's. I do that all the time. My students are always like, Miss Graves, you forgot the dx. So now we have this. We can also factor out a pi to simplify it even more. We don't need to be worrying about that pi when we're doing stuff. So minus x squared plus 1 quantity squared dx. So notice this pretty formula. This is our smaller radius. This is our larger radius. This is our height, and we still have pi out front here. I tell my students this is a great formula to keep in hand. So we write it over here in a more generalized form. Volume of a washer is equal to pi times your bounds here, A to B, whatever, your points of intersection of your region is made by there. And then you take your radius of your larger one, quantity squared, and you subtract off the radius of your smaller one, quantity squared, and you do it with respect, in this case, to dx. In the future, we'll learn how to do dy, which would be revolving around the y-axis or revolving around a line, whether it's an x equals line or a y equals line, vertical or horizontal. The final answer for this one, should you want to put it into your calculator, you should feel free. Again, the pi is out front because most teachers want you in exact form. And then you plug this portion into your calculator. It's going to give you the answer in probably a decimal form. You can hit that fraction button and find out that it's 1/17 over 5. And then we multiply that by pi. And then we write units cubed because volume's always cubed. So this is our final answer for this problem. This is the formula that you should hang on to. And I hope this has been helpful for you today. If it is, definitely click on the next link to get you to revolving around the y-axis and revolving around horizontal and vertical lines. Have a great day.